Welcome to DAR Tutors, your trusted source for online and home tuition. In this video, we will explore the fundamental concepts of proton transfer reactions, a key topic in IB chemistry higher level. Our objective is to provide a clear and rigorous understanding of acids, bases, and their interactions, aligning perfectly with the IB syllabus. Let's begin by establishing the basic definitions. We'll start with the Arrhenius definitions of acids and bases. An Arrhenius acid is a substance that produces hydrogen ions, or H+, when dissolved in water. A classic example is hydrochloric acid, or HCl. When HCl gas is dissolved in water, it ionizes to produce hydrogen and chloride ions. The equation is HCl aqueous gives H plus aqueous plus Cl minus aqueous. This release of hydrogen ions is the defining characteristic. Similarly, we can look at sulfuric acid, or H2SO4, which is a diprotic acid, meaning it can donate 2 protons. Here, H2SO4 aqueous yields 2 H plus aqueous ions and 1 SO42 minus aqueous ion. Now let's consider the Arrhenius base. An Arrhenius base is a substance that produces hydroxide ions, or OH minus, when dissolved in water. A common example is barium hydroxide, BOH2. Barium hydroxide in aqueous solution dissociates to form 1 barium ion, Ba2 plus aqueous, and 2 hydroxide ions, OH minus aqueous. The presence of these hydroxide ions is what makes the solution basic. It's crucial to understand that according to the Arrhenius theory, acidic or basic properties are only exhibited in aqueous solutions because that's where ionization can occur. We have now defined acids as H plus donors and bases as OH minus donors within the context of water. While the Arrhenius theory is a good start, it has limitations. A more comprehensive model for HL chemistry is the Bronsted-Lowry theory. The fundamental concept of the Bronsted-Lowry theory is the transfer of a proton. A Bronsted-Lowry acid is defined as a proton donor. In this context, a proton is a hydrogen ion H+, which is just a hydrogen atom that has lost its single electron. Conversely, a Bronsted-Lowry base is defined as a proton acceptor. Bases must have at least one lone pair of electrons to form a coordinate bond with the proton. A major improvement of this theory is its broader applicability. It doesn't require an aqueous solution. It applies to all solvent systems and even to gas phase reactions. Let's illustrate this with the reaction between ammonia gas and hydrogen chloride gas. The equation is NH3 gas plus HCl gas gives solid NH4Cl. In this reaction, the HCl donates its proton to the NH3. HCl is the proton donor, so it is the Bronsted-Lowry acid. NH3 accepts the proton, making it the Bronsted-Lowry base. Notice this reaction doesn't involve water, yet it's clearly an acid-base reaction. By adopting the Bronsted-Lowry definition, we can analyze acid-base reactions in a more general and powerful way. An essential concept stemming from the Bronsted-Lowry theory is the conjugate acid-base pair. In any acid-base reaction, there are always 2 conjugate acid-base pairs. Each pair consists of 2 species that differ by a single proton. Let's consider the ionization of chloric saponific acid HClO4 in water. The equation is HClO4. Aqueous plus H2O liquid is in equilibrium with H3O plus aqueous plus ClO4 minus aqueous. In the forward reaction, HClO4 donates a proton to H2O, so HClO4 is the acid and H2O is the base. When HClO4 loses a proton, it forms the ClO4 ion. This ion is now capable of accepting a proton, meaning it can act as a base. We call ClO4 the conjugate base of HClO4. Thus, HClO4 and ClO4 form a conjugate acid-base pair. Similarly, when H2O gains a proton, it forms the H3O plus ion. This ion can donate a proton, so it's an acid. We call H3O plus the conjugate acid of H2O. Therefore, H2O and H3O plus also form a conjugate acid-base pair. In summary, a base's conjugate is its protonated form, and an acid's conjugate is its deprotonated form. This framework allows us to analyze the acid-base properties of both reactants and products. Some species have a fascinating property. They can act as both an acid and a base. These are called amphiprotic species. Amphiprotic species are capable of accepting a proton, thus behaving as a Bronsted-Lowry base, and also capable of donating a proton, thus behaving as a Bronsted-Lowry acid. The classic example is water, H2O. We just saw it act as a base in the reaction with chloric C7 acid. Now let's see it act as an acid with phenylamine, C6H5NH2. The equation is C6H5NH2. Aqueous plus H2O liquid is in equilibrium with C6H5NH3 plus aqueous plus OH minus aqueous. Here, water donates a proton to the phenylamine. Water is the proton donor, so it acts as an acid. Phenylamine is the proton acceptor, so it acts as a base. So, water is amphiprotic. Its behavior depends entirely on the other species in the reaction. Another important class of amphiprotic species are the conjugate bases of polyprotic acids. Consider the hydrogen carbonate ion, HCO3, which comes from the diprotic carbonic acid, H2CO3. HCO3 can act as an acid. For instance, with a strong base like hydroxide, it donates a proton to form the carbonate ion, CO32-. But HCO3 can also act as a base. With a strong acid like hydronium, it accepts a proton to reform carbonic acid, H2CO3. Therefore, the hydrogen carbonate ion is also amphiprotic. We've seen how water and ions from polyprotic acids can exhibit amphiprotic behavior, acting as both proton donors and acceptors. A central application of acid-base chemistry is the neutralization reaction, which forms a salt. Neutralization is the reaction between an acid and a base to produce a salt and water. The key characteristic is that the salt is the only non-water product. The salt is an ionic compound formed when the hydrogen ion of the acid is replaced by a cation, usually from a metal or ammonium. Let's work through an example, the reaction of sulfuric acid with barium hydroxide. We have H2SO4 aqueous reacting with BaOH2 aqueous to produce BaSO4 solid and 2 molecules of H2O liquid. The salt formed is barium sulfate, BaSO4. In this case, it's an insoluble salt, which precipitates out of solution. To get a clear picture of what's happening, we can write the net ionic equation. First, we write the full ionic equation. H2SO4 is a strong acid, so it completely dissociates into 2H+ and SO42-. BaOH2 is a strong base, so it dissociates into Ba2+ and 2OH-. The products are the solid BaSO4 and water. Now we identify spectator ions. These are ions that are present in solution but do not participate in the reaction. Notice that the sulfate ion, SO42-, appears on both sides. It's a spectator. The barium ion, however, is removed from solution as part of the precipitate. The H+ and OH- combine to form water. By removing the spectator ion, we get the net ionic equation, which represents the essential chemistry. The net ionic equation is 2H+ aqueous plus Ba2+ aqueous plus 2OH- aqueous gives solid BaSO4 and 2H2O liquid. This equation highlights the two main processes occurring: the formation of water from hydronium and hydroxide ions, and the precipitation of barium sulfate. This method simplifies complex reactions by focusing on the species that actually change. Salts can be prepared in a variety of ways, depending on their solubility and the nature of the reactants. We'll explore two key methods. The first method is for preparing insoluble salts. A prime example is barium sulfate, BaSO4, which we just discussed. Insoluble salts are prepared using the precipitation method. Here's the process. First, we need 2 soluble salts that contain the ions we want. For BaSO4, we could use barium chloride, BaCl2, and sodium sulfate, Na2SO4. Second, we mix the aqueous solutions of these 2 salts. The ions combine to form the insoluble salt, which precipitates out of the solution. The equation is BaCl2, aqueous plus Na2SO4. Aqueous yields BaSO4 solid plus 2 NaCl. Aqueous. Third, we separate the precipitate. We use filtration to collect the solid BaSO4 and leave the soluble NaCl in the filtrate. Finally, we wash the precipitate with distilled water to remove any impurities and dry it. This 3-step process, mixing, filtration, sauen, and drying, is the standard method for producing pure, insoluble salts. The second method is for preparing soluble salts where the parent base is soluble. This requires a titration. Let's say we want to prepare sodium chloride, NaCl, from hydrochloric acid, HCl, and sodium hydroxide, NaOH. The reaction is HCl aqueous plus NaOH aqueous yields NaCl aqueous plus H2O liquid. First, we perform an acid-base titration. We carefully add the acid to the base, or vice versa, using an indicator to determine the exact volume needed for complete neutralization. This is the equivalence point, where moles of acid equals moles of base. Second, we repeat the titration, but this time without the indicator. Indicators are acids or bases themselves, so adding them would contaminate the product. Third, we take the resulting neutral solution and heat it to evaporate the water. The soluble salt, sodium chloride, will then crystallize out of solution. Finally, we filter off the crystals and dry them. The steps for preparing a soluble salt by titration are to find the equivalence point, then repeat the neutralization and crystallize the salt from the pure water. By understanding these two methods, we can prepare a wide variety of salts, both soluble and insoluble, in a pure form. Now let's delve into the different types of salts that can be formed, especially from acids that have more than one replaceable hydrogen atom. We define the basicity of an acid by the number of protons it can donate. Monoprotic acids donate 1 proton. Diprotic acids donate 2 protons, and triprotic acids donate 3. Monoprotic acids, like HCl or HNO3, always form one type of salt, where the single hydrogen is replaced by a metal cation. These are called normal salts. Polyprotic acids, which are acids with a basicity of 2 or more, can form different types of salts depending on whether all or only some of their protons are replaced. A normal salt is formed when all of the replaceable hydrogens in a polyprotic acid are replaced by a cation. For example, sodium sulfate, Na2SO4, is a normal salt of the diprotic acid, H2SO4. However, polyprotic acids can also form another type of salt called an acid salt. An acid salt is formed when only some of the replaceable hydrogens of a polyprotic acid are replaced by a cation. In other words, the salt ion still contains one or more acidic hydrogens. Let's take carbonic acid, H2CO3, as an example. It's a diprotic acid, so it has 2 replaceable hydrogens. It can form the normal salt sodium carbonate, Na2CO3, where both protons have been replaced by sodium ions. The reaction for its formation is H2CO3 plus 2NaOH to give Na2CO3 plus 2H2O. Here both hydrogens are gone, so it's a normal salt. But it can also form the acid salt, sodium hydrogen carbonate, NaHCO3. In this case, only one of the 2 protons is replaced by a sodium ion, leaving one acidic hydrogen in the hydrogen carbonate anion, HCO3. The reaction is H2CO3 plus NaOH to give NaHCO3 plus H2. Phosphoric acid, H3PO4, is triprotic, meaning it has 3 replaceable hydrogens. This allows it to form a normal salt, a hydrogen phosphate, and a dihydrogen phosphate. With 1 mole of NaOH, it forms sodium dihydrogen phosphate. With 2 moles of NaOH, it forms sodium hydrogen phosphate. And with 3 moles of NaOH, it forms the normal salt sodium phosphate. Understanding basicity helps predict the possible salt formations. We've seen how to distinguish between normal and acid salts based on the complete or partial replacement of hydrogen atoms. A key skill in chemistry is being able to work backward and identify the parent acid and parent base that formed a particular salt. The general principle is to reverse the neutralization reaction. To find the parent base, add hydroxide ions to the salt's cation. To find the parent acid, add hydrogen ions to the salt's anion. Let's work through a couple of examples. First, consider the salt ammonium phosphate with the formula NH4,3PO4. Step 1 is to separate the salt into its component cation and anion. In this case, we have ammonium ions, NH4+, and phosphate ions, PO43. To find the parent base, we look at the cation NH4+. We add a hydroxide ion, OHE, to it. This forms ammonium hydroxide, NH4OH, which in solution is aqueous ammonia. This is our parent base. So NH4 plus OH gives NH4OH, or NH3 aqueous. Parent base found. Next, to find the parent acid, we look at the anion, PO43. The charge is 3-, so we need to add 3 protons, or 3H+, to neutralize it. Adding 3H+ to PO43 gives H3PO4, which is phosphoric V acid. This is our parent acid. 3. Parent acid from anion 3 plus plus 4 3 itaroba 3 4 AQ. So the parent base is aqueous ammonia and the parent acid is phosphoric acid. They combine to form ammonium phosphate. Let's try another one, lithium sulfate, Li2SO. First, we separate it into its ions, lithium ions, Li+, and sulfate ions, SO42. For the parent base, we take the cation Li+, and add one OH ion. This gives LiOH, lithium hydroxide. This is our parent base. For the parent acid, we take the anion SO42. The 2- charge means we need to add two H+ ions. This gives H2SO4 sulfuric acid. This is our parent acid. This process is a fundamental skill for understanding salt hydrolysis, which we will cover in a later topic. We've now seen a systematic approach to identifying the acid and base components that form any given salt. We have now reached the 10-minute mark. If you find this style of clear, concept-driven explanation helpful, we encourage you to contact DAR Tutors. We offer expert tuition in IB, A-Level, and IGCSE curricula, providing the support you need to excel. Visit our website or call us to learn more. Again, if you appreciate this detailed approach, contact DAR Tutors for personalized tuition in IB, A-Level, and IGCSE. To solidify your understanding, let's practice with some IB-style questions. First question, which of the following compounds is amphiprotic? Take a moment to consider the definition of amphiprotic and analyze each option. The correct answer is C, HPO42-. Let's see why. HPO42 can donate a proton behaving as an acid to form PO43. It can also accept a proton behaving as a base to form H2PO4. HCl and CH3COOH are acids, and NH3 is a base. They cannot act as both. So HPO42 is amphiprotic because it can both donate and accept a proton. The answer is C. Here is our second question. Identify the parent acid and parent base of the salt, NH42SO4. Remember the process we just learned. Identify the cation and anion, and then add OH- to the cation and H+ to the anion. The cation is ammonium, NH4+. Adding OHE gives ammonium hydroxide, which is aqueous ammonia. So the parent base is NH3 aqueous. The anion is sulfate. 42. The 2- charge means we need to add 2H+ to form the parent acid, which is H2SO4 sulfuric acid. The parent acid is H2SO4. Therefore, the parent acid is sulfuric acid and the parent base is ammonia. Let's continue with our practice questions. Question number 3. A student mixes 25 semi-3s of 0.10 m barium hydroxide with 25 semi-3 of 0.10 m hydrochloric acid. Will the final solution be acidic, basic, or neutral? This question requires us to think about stoichiometry in acid-base neutralization. It's a common mistake to assume that mixing any acid and base results in a neutral solution. Let's analyze it. First, let's write the balanced chemical equation. Barium hydroxide reacts with hydrochloric acid to produce barium chloride and water. The equation is BeOH2. Aqueous plus 2HCl aqueous yields BaCl2 aqueous plus 2H2O liquid. Notice the stoichiometry. 1 mole of barium hydroxide reacts with 2 moles of hydrochloric acid. Now let's calculate the moles of each reactant we are mixing. We calculate moles using the formula concentration times volume. For barium hydroxide, moles are 0.17 moles per dm3 times 0.025 dm3, which equals 0.0025 moles. For hydrochloric acid, moles are 0.1 moles per dm3 times 0.025 dm3, which is also 0.025 moles. Based on the balanced equation, 0.025 moles of barium hydroxide would require 2 times 0.025, or 0.0050 moles of HCl for complete neutralization. Required HCl equals 2 but our positive 25 mol Bay OH2 equals 0.050 mol HT. However, we only added 0.0025 moles of HCl. This means that hydrochloric acid is the limiting reactant and barium hydroxide is in excess. Since the base, barium hydroxide, is in excess, the final solution will contain unreacted hydroxide ions. This will make the solution basic. This question reinforces the importance of using stoichiometry to determine the outcome of a neutralization reaction. The answer is basic. Let's move on to our fourth practice question. Consider the reaction H2O plus HCO3 minus in equilibrium with CO32 minus plus H3O plus. For the reverse reaction, identify the Bronsted-Lowry acid and base. This question tests your understanding of conjugate acid-base pairs in equilibrium. Remember that conjugate acid-base pairs always exist on opposite sides of a reaction. The question specifically asks about the reverse reaction. Let's write that out. The reverse reaction starts with the products of the forward reaction. So it's CO32 minus aqueous plus H3O plus aqueous in equilibrium with H2O liquid plus HCO3 minus aqueous. Now we identify the proton donor and acceptor in this reverse reaction. Looking at the products, HCO3 minus has one more proton than CO32 minus. This means that H3O plus must have donated a proton to CO32 minus to form these products. Therefore, H3O plus is the proton donor, making it the acid, and CO32 minus is the proton acceptor, making it the base. Alternatively, you could first identify the conjugate pairs in the forward reaction. In the forward reaction, H2O is the base, and H3O plus is its conjugate acid. HCO3 is the acid, and CO32 is its conjugate base. In the reverse direction, the conjugate acid and base simply switch their roles. So the acid is H3O+, and the base is CO32 for the reverse reaction. The answer is hydronium ion for the acid and carbonate ion for the base. Our final practice question is a bit more complex, involving an acid salt. Question 5. Write the balanced chemical equation, including state symbols, for the reaction between hydrobromic acid and calcium hydrogen carbonate. First, we need to determine the formulas of the reactants. Hydrobromic acid is HBr. Calcium hydrogen carbonate consists of a calcium ion, Ca2+, and two hydrogen carbonate ions, HCO3, giving the formula KaHCO3-2. Recall that acids react with carbonates and hydrogen carbonates to form a salt, water, and carbon dioxide gas. So, the products will be a calcium salt, water, and carbon dioxide. The salt will be formed from the cation Ca2+ from the base and the anion bromide from the acid. Since calcium is 2+ and bromide is 1-, we need two bromide ions, making the salt calcium bromide, KBr2. So far, our unbalanced equation is HBr plus KaHCO3 Carbon2, KaBr2 plus H2O plus CO2. Now we balance the equation. We have two hydrogen atoms from the hydrogen carbonate. We need two hydrogens from the HBr to react. This also gives us two bromides for the KaBr2. This gives us two HBr. Balancing the carbons and oxygens on the right requires two water molecules and two carbon dioxide molecules. Let's double-check the balance. Reactants 4H, 2Br, 1Ca, 2C, 6O. Products 4H, 2B, 1Ca, 2C, 6O. The equation is balanced. Finally, we add state symbols. Hydrobromic acid and calcium hydrogen carbonate are typically aqueous solutions. Calcium bromide is a soluble salt, so it is also aqueous. Water is liquid and carbon dioxide is a gas. This question required combining knowledge of acid-base reactions, salt formation, balancing equations, and state symbols. We have successfully derived the full chemical equation. To recap, we have covered the Arrhenius and Bronsted-Lowry theories, the concept of proton transfer, and conjugate acid-base pairs. We also explored neutralization reactions, the formation and naming of salts, and methods for salt preparation. These fundamental principles are the cornerstone of acid-base chemistry in the IB curriculum. Thank you for watching this Dart Tutors video. For more personalized and expert guidance, please contact us. We hope this detailed explanation has been beneficial. For further assistance, contact Dart Tutors.